All right, let's get right into it. So your application has gone global, which is amazing. But now you're staring down a massive challenge. How do you make sure a user in Tokyo gets the same incredible lightning-fast experience as someone sitting in Toronto? That's what we're here to figure out. Today, we're going to architect a routing strategy that's not just fast, but resilient enough to handle the chaos of the real world.
So here's the game plan. First, we'll dig into the core problem we're all trying to solve. Then, we'll pop open the routing toolkit and look at the main tools we have to work with. After that, we'll get our hands dirty and actually build a practical multi-cloud architecture. And, things always go wrong, so we'll plan for that. Finally, we'll wrap up with some common mistakes you definitely want to avoid.
So let's really set the scene here. Your app isn't just a local hero anymore, it's playing on the world stage. And what that really means is that every single user, no matter where they are on the planet, is expecting a perfect, seamless, and most importantly, instant connection.
And this is the fundamental question, isn't it? You've got users coming from every corner of the globe, all hitting that one domain, yourapp.com. How on earth do you make sure their experience isn't totally tanked just because of where they live? The goal here is simple to say, but hard to do. A consistent, fast experience for everybody, everywhere.
Okay, so how do we even begin to solve this massive global puzzle? Well, it turns out we have two main tools in our belt, and it really all boils down to a classic battle: latency versus location. Or you could think of it as speed versus geography. Knowing which tool to use and when is pretty much the secret to a brilliant design.
Our first tool is latency-based routing. You can think of this as the performance-first approach. It's obsessed with one thing and one thing only: speed. The system doesn't care if the user is in Paris or Peru. Its only mission is to find the absolute fastest, lowest latency network path from that user to one of your servers.
But wait a minute, how do we even know what's fastest?
Good question. There are basically two ways to do it. The first is active measurement, where we send out these little digital scouts, or probes, from all over the world to time how long it takes to get to your servers and back. Or we can do it passively, by just watching the real user traffic as it flows in, and using that data to build a live map of internet performance.
And this brings us to a super important point, something that trips up a lot of people. You would think that the server that's physically closest is always the fastest, right? Wrong. The internet is a tangled, messy web. Things like weird routing paths and congested networks mean that a server halfway across a continent might actually be faster for a user than one in the next city over. Never, ever assume that geography equals speed.
Now for our second tool, geo-based routing. This one's way more straightforward. Instead of chasing the lowest latency, we just look at where the user's request is coming from, their country or their continent, and we send them to a server we've already designated for that region. It's not about dynamic performance. It's about following a set of geographic rules.
So you might be wondering, why would I ever pick rules over pure speed? Well, a lot of the time you don't have a choice. Geo-based routing is absolutely critical for things like data residency laws. Think GDPR, where you're legally required to keep European user data inside Europe. Or maybe it's for content licensing, like a streaming service that only has the rights to show a movie in specific countries. It's all about creating predictable and often legally required guardrails.
All right, that's enough theory. Let's get practical. Let's take these tools and see how they come together to build a real, working, multi-cloud architecture that can actually serve a global audience.
Okay, so here's our setup. We have one SaaS application, but to make it global, we've deployed it across 3 different clouds. We're running on AWS in North America to cover the Americas. We're using Azure in Europe to serve everyone in Europe and Africa. And we've got GCP in Asia to handle the entire Asia-Pacific region.
So let's follow a single user's journey. Let's say someone in Germany opens their laptop and types in yourapp.com. First, their request hits our global traffic management layer. That system, using its latency measurements, instantly sees that for this user, the Azure endpoint in Europe is the fastest, healthiest option available. So it hands the IP for that Azure server back to the user's browser, and boom, they're connected. They have no idea that a complex, high-speed decision just happened in milliseconds. It just works.
Building an architecture that works perfectly on a sunny day is one thing. But a truly resilient architecture is one that's designed from the ground up to handle the inevitable storms.
So what happens when that Azure region in Europe just goes dark? A whole region can fail. It happens. Now, when our user in Germany tries to connect, where do they go? If we don't have a plan, the answer is nowhere. Your app is down for an entire continent. That's a disaster. We've got two main playbooks for handling this kind of failure. The first is DNS failover. Our traffic manager sees the outage in Europe and just starts giving out the IP for our AWS deployment in North America instead. It works, for sure, but it can be slow to kick in because of the way DNS caching works. The other option is a global load balancer. It reacts much, much faster, but you have to be careful because the load balancer itself can become a single point of failure. It's a classic trade-off between speed and stability.
Of course, none of this failover magic works if you're flying blind. You have to have visibility. You need to be monitoring everything all the time. The latency to each region, the error rates at each endpoint. You even need to know if your health checks are giving you false positives. Without good data, you're not making decisions, you're just guessing.
And that brings us to one of the most critical and yet most often ignored settings in this whole setup, your DNS time to live, or TTL. This little number tells browsers and servers how long they should remember a DNS answer. Now, if your TTL is set to, say, an hour and your European region fails, users will keep trying to connect to that dead server for up to an hour. That's why a low TTL, like 60 seconds, is absolutely vital for making sure your failover actually happens quickly.
All right, to wrap this all up, let's quickly go over some lessons learned the hard way. These are the common anti-patterns, the pitfalls that you want to actively avoid when you're designing your own global routing strategy.
First, don't use geo-routing and expect it to be the fastest. We've already busted that myth. Second, don't just assume that a fancy anycast network is some kind of magic bullet that solves everything. It's got its own quirks. We just talked about DNS TTL. Please don't ignore it. This is a big one. Don't build a crazy complex global system before you even have global users. And finally, the most important one of all, you have to test your failover regularly. If you don't test it, you don't have a plan, you just have a hope.
So I want to leave you with this one final question to think about for your own systems. Take a hard look at what you've built. Is it a strategy that's truly resilient, one that can adapt and flex and absorb the chaos of a real-world outage? Or is it just rigid? Does it look great on a whiteboard, but is it brittle enough to shatter the first time something unexpected happens? The answer to that question makes all the difference in the world.